2x minus 5 minus minus 2 must be less than epsilon. Okay, so now we'll take our premise and we'll work it through. So now what we know is, so therefore what we have is that the absolute value of x minus 1 must be less than uh, epsilon over 5. Okay, so the absolute value of x minus 1 must be less than epsilon over 5. Now, we also know that, don't forget, we really need to get this into this particular form here. So we really need to introduce back in the quadratic, yeah? Okay? But don't forget what we had earlier on. Uh, Note that x plus 3 is less than 5. Okay, x plus 3 reaches its maximum around 5. So therefore, this implies that x minus 1 times x plus 3 must be less than, okay, uh, epsilon over 5, okay, times 5. Okay, well, what's this imply? This implies that x minus 1 times x plus 3, okay, must be less than epsilon. And you can see this is working out perfectly for us now. This implies that x squared plus 2x minus 3 is less than epsilon. And once again, we want to get our limit out here, and our limit is going to be our minus 2. So this implies that x squared plus 2x, uh, x squared plus 2x minus 5 plus 2, so minus 5 plus 2 is our minus 3, is less than epsilon. And this implies that x squared plus 2x minus 5, which is our function, minus minus 2, which is our limit, is less than epsilon. What did we end up with here? We've ended up with f of x minus L is minus 2 is less than epsilon. So going from our premise, okay, which is that x minus a is less than delta, we've just shown that under the restriction, under the case where the minimum delta is epsilon over 5, we've just actually shown that what we end up with is f of x minus L is less than epsilon. Now, just to go back here, so the key part of this particular proof when it comes to quadratics is that typically we end up with a situation where when we try to figure out an appropriate delta, and don't forget, our technique for finding an appropriate delta is we'll always start with the conclusion and work the conclusion down to get it into a shape that looks like the premise, okay? Because we know that the conclusion has to be less than epsilon. So if we work this piece down here so that it gets to something that looks like the premise, we're going to end up with something that's less than some function of epsilon, okay? Now, the trick here in this particular case is that when we took f of x minus L less than epsilon, the conclusion, and when we worked it down, we ended up getting the premise less than a specific value. But this specific value was dependent on epsilon and also on x plus 3, and we only wanted dependent on epsilon. So what we needed to do is we needed to figure out what the hell was going on here with this particular x plus 3. And one thing that we do know from our limit is that the limit L, that the function approaches the limit near A. So let's restrict our concentration to somewhere near A. And in fact, let's make delta to be less than, let's make delta to be less than 1. So within 1 unit of A is really what we're looking at. Now, when we go to 1 unit in A, what we're trying to do is we're trying to figure out what's happening with x plus 3. We know what's happening with x minus 1, okay? But from this particular restriction, what we end up with is x plus 3 is bounded below and above by 3 and 5, okay? But the key point here is this, is that any number divided by a small number, okay, will give us a bigger number relative to any number divided by a bigger number, okay? So we want to make epsilon as small as possible, or we want to make our delta as small as possible. So we restrict now to x plus 3. We consider x plus 3 that's near 5, which is going to be making that smaller than it would be if we had have chosen 3. So in this case, our new delta will be epsilon over 5. So now we have two cases when the delta is 1 and when it's epsilon over 5. Okay, and what we're going to do is we're just going to choose the minimum between these two. We've got two cases. We need to evaluate it for when one is actually the minimum, and then we need to evaluate when epsilon over 5 is the minimum. And that's what we've basically done here, is we took the case when delta is equal to 1, and then we took the case when delta is equal to 2. Okay, guys. I mean, there was a lot of work involved in that. I think I will do another couple of these quadratics just so that you can actually see the process, see what's going on, and I think when you do the evaluation really helps you to understand the actual that complicated definition associated with a limit. Okay, guys. Once again, this is Jonathan Lambert with Maths and Stats. And this video, another video in our series of videos dealing with calculus and limits and epsilon delta proofs. I hope that this video was in some way intuitive, and more importantly, I hope that was helpful for you. And thanks for watching. Okay, bye bye.